Hello, my name is John Hedengren at Brigham Young University, and I'm going to be talking a little bit about managed pressure drilling automation, some challenges and opportunities with high-speed data. So first of all, why automate drilling? What are the opportunities? We're going to talk about some new physics-based models and also improved high-speed telemetry. So wired drill pipe or other methods to be able to access downhole data. We're also going to review lower-order models and some of the progress there. Sometimes the large models can't be used directly. We'll go over a couple of simulation studies and then also talk about a new way of thinking, combining pressure control and rate optimization. We'll also talk about multivariable predictive control, a little bit more of an advanced topic, and then a couple automation case studies, offshore Southeast Asia and Latin American land. So first of all, why automate drilling? The benefits of automating drilling, first of all, are health, safety, and environment. Faster response to problems. You take a light touch versus a major response, or something like closing in the well when there's a big problem, to something like a gas influx. Economic as well. You can operate closer to constraints. There's a shorter drilling time, especially with challenging market conditions that currently exist. We have an opportunity to drill faster. The other reason that continues to be a problem, even after the BP Macondo well blowout, is that there continue to be about an average of 4 uncontrolled well situations in the Gulf of Mexico each year. And that was done, reported in these studies. So we're still having some of those same issues, maybe not quite the same results, but some of these uncontrolled well situations are still happening. We also want to talk about benefits of advanced control. So having computers adjust valve positions, pumps, chokes, and pumps. Okay, so first of all, what are the opportunities? What's changed in the last couple of years? And I'll suggest 3 things that have changed. And the first one is high fidelity modeling, indicated by one thing coming into this funnel. We have some very good wellbore hydraulic models and also drillstring dynamic models. That have been developed over the last few years and also validated with drilling data. The next is optimization algorithms. Be able to solve these models faster and be able to optimize them. So with some of the optimization benchmarks, we've seen that we can solve some of these same problems 15 years ago. We can solve them 1,000,000 times faster, and that's due to software and hardware improvements. The third thing that we're going to be talking about is high-speed drill string telemetry, the ability to measure what's actually going on downhole. And we can do that with wired drill pipe, and also the sensors, advancements in sensors that are placed downhole as well. Okay, so first of all, the need for physics-based models. There's a lot of reasons why you might want to develop or employ physics-based models in your organization. Everything from planning to training scenarios, operations, or after-action review. The thing that we're going to be talking about here is more in the center, the well control, and rate of penetration. And be able to control pressure and also maximize rate of penetration. Okay, so automation and control is one of the reasons for doing this. And although I'm focusing on this today, there are many other reasons why you'd want to have a fit-for-purpose simulator for drilling operations. So let's talk about advances in some of these physics-based models. Many of the advances have happened with complex models in wellbore hydraulics and drill string dynamics. There is a publication here that you can look to for further information. But basically the bottom line is, if we can reproduce a lot of these drilling scenarios with simulators, and those who have spent a lot of time drilling agree that the fidelity of the simulators is getting better. We also have drill string dynamic models as well. So this slide highlights that. You can see a stiff string right here, where it has interaction between the string and the well bore. You can see some backward whirl developing here in simulation, okay, as it proceeds. So we can simulate some of these vibration modes that happen in practice, or whirl or other types of events. Okay, so simulators have advanced quite a bit in the last couple of years, but sometimes the simulators don't exactly represent what's happening in the in downholes, and so there's many times where we need to or want to measure what's happening downhole. Okay, and so that's where wired drill pipe and advances there have come in, and we can see here, we can see a I'm going to go ahead and just with wired drill pipe is up here in terms of data transmission rates, and this is on a log scale right here in terms of the data transmission. You can see mud pulse technology, and so over the years the mud pulse technology has improved, data compression, other things, and electromagnetic telemetry, acoustic signals, and it's really just been within the last couple of years that there's really been this step change, orders of magnitude improvement in terms of the data transmission rates. So advances in telemetry, there's been a lot of improvements in the reliability. That was one of the weaknesses before, that went from, let me go back a slide here, back in 2012, maybe about a 60% reliability, up to about 98% reliability. So some of the improvements there are cable reliability improvements, okay, resistance to things like stress crack corrosion and others. There's been improvements in downhole network electronics improvements, so the ability to self-diagnose where the problem is, be able to identify the section that's bad. Surface network electronics improvements, okay, so interfaces with tools and be able to transmit that data. So these are some of the advances that have taken place. A little bit more information is here if you're interested. Okay, so nonlinearity in drilling is a big issue, and as we talk about managed pressure drilling, you can see that a very small change in choke valve in this region has a very large effect. Okay, the slope is very steep here, but it doesn't have a lot of effect in this region. Okay, so when the valve is nearly closed, we have this very, very strong effect. Very small changes in the valve are going to have a big effect in the downhole pressure. So it's very nonlinear, and this is part of what makes it very challenging. Okay, so we have these high fidelity models. We have, this data transmission. The data or the models aren't really going to do us a lot of good in real-time drilling unless we can use them. And so this highlights the need for lower order models that can solve fast and reliably, and are going to be able to track most of the things that we're interested in with the hydraulics and the drill string dynamics. Okay, so in managed pressure drilling, these are the things right here that we can typically change: the pumps and the chokes. Okay, we have a back pressure pump as well. And then the things that we're trying to maintain at levels are bottom hole pressure, annular pressures, the pressure at the casing shoe, these types of things that we want to try to maintain. Okay, and the things that we don't necessarily know are things like the fluid density. Sometimes we can't measure that directly. The annulus friction factor as well relates to how much pressure drop you have as you flow. Also, you have non-Newtonian fluids, which also can affect that. And then also reservoir pore pressure, especially if you're trying to match a reservoir pore pressure in managed pressure drilling. So we want to be able to match these physics-based models, these really fundamental, a lot of equations, with lower order models that might only have 7 equations or so. Now here are some simulations that show changes in the choke valve pressure and also the mud pump pressure. Okay, so as the mud pump increases or decreases, or the choke valve opens or closes, how that's going to affect the downhole pressure. We can see there's excellent match here as we train these in the beginning. This is like a training period, okay, over the first few seconds as we receive this data, and we match to these. We can match to these high fidelity, these physics-based models. Okay, so as we have these lower order models, they're fast, they're reliable, they can solve real time. We can think about how to implement these. Now, one way is with a conventional feedback controller. And I'd like to make an analogy here that it's kind of like driving in your car looking backwards. Okay, so you're responding to disturbances as they come. Let's say you notice that you're starting to veer off the road, you respond. Okay, now in the other case, you have predictive control, where you use these models to say, if I do something now, how is that going to affect me 1 minute, 10 minutes, 30 minutes from now? And that is plans a path for your chokes and pumps into the future to get you to a desired state. Okay, that might be a desired state right here in terms of a pressure. Okay, so that's like looking forward while you're driving. Okay, so let's just do a quick comparison here with conventional control. Now this is the looking backwards one, and we're only using the choke opening here. And you can see that we're wanting to have different pressures here at the bottom hole, and we're maintaining a constant mud pump. Now, due to the nonlinearities, the valve is is opening and shutting there quite a bit. Okay, so some pretty aggressive action on the choke to try to meet those set points. Now with we have another one here. So let me go ahead and erase these. Okay, so now if we use predictive control, we can use both the pumps and the chokes in a coordinated fashion to help us reach the desired levels faster and stay on target better. Okay, we can put in constraints, like we wouldn't want the mud pump to go below a certain amount, maybe for cuttings loading issues. But you can see much less movement here in the choke because we're coordinating the actions with the pump. Okay, so we have improved connections and kick response. This shows during a pipe connection procedure, we ramp down the pumps and the choke, turn on the back pressure pump, and there you can see it's coordinated with this back pressure pump. So the back pressure pump comes on, so there's always flow going through the choke valve. Okay, and then we have excellent excellent pressure control. Now this is all in simulation. I'm going to show some results as well where this is actually applied in the field. But this is in simulation, shows that we can maintain plus or minus 1% on our pressure. Okay, and some additional information there if you'd like to go see that. Okay, we have objectives of trying to maintain within plus or minus 1 bar during normal drilling operations, and typically within plus or minus 5 bar during pipe connection procedures. Now this depends on the objectives of the well and other things that are happening, but these are our typical targets for pressure control while drilling with MPD. Okay, so I want to talk about maybe a new way of thinking. We've talked about pressure control. Some of these ideas are fairly standard. We'd want to use, be able to anticipate changes coming. I'm going to introduce a new way of thinking about some of these things that's quite different from the way it's currently done. So if we think about, for example, pressure control and rate of penetration maximization. Okay, we always want to try to maximize up to allowable levels, the rate of penetration. So these two are they're currently separate applications. We try to maintain pressure control with the chokes and pumps, and we try to maintain rate of penetration with weight on bit and RPM, the rotation rate of the drill string. Now what happens if we combine those two? Okay, so this might be pressure control, and this might be rate of penetration, but what if we put those together into a single application? Let's see what happens. Okay, first of all, we have to combine these models together. So we have some examples of, a lot of work that's been done on drill string hydraulics and also drill string dynamics, and the effect on rate of penetration. Okay, and again, some additional information there. Okay, so if we think about automated kick response, so you're drilling MPD, and you enter a region with higher pore pressure, and you start to receive a gas influx. Now, the former way of doing this is shown here in the black. Okay, that would be like a manual response, be able to catch the kick after a period of minutes or hours. You notice a pit gain or something like that happening, and you would respond to it. Okay, by closing the choke, increasing the pump rate, circulate out the kick. Okay, now with automated controllers, okay, we're able to decrease this response time, improve the response time, and if we have in the red, it shows this comprehensive controller. So that's if we combine these two controllers, and the reason why we can do that is because rotation rate has a big effect on pressure as well. And so simultaneously, while trying to minimize this kick, you are increasing the rotation rate and decreasing weight on bit, maintaining rate of penetration, but also at the same time using those two to respond to the kick. Okay, so this is a new way of thinking about pressure control and rate of penetration in a coordinated way that uses these models. Okay, and one other thing that we notice is if we do this, we can also lower the pressure right at the bit to the allowable limit, and that also helps us achieve a higher rate of penetration. So the pressure and the rate of penetration control are connected. Okay, so one of the challenges of automation is that it can become unreliable if the control model is not calibrated or is not sufficiently accurate. So this is a known issue: model accuracy, controller stability, and there's some recent developments in this area as well that have addressed these issues, especially with ensemble models. Okay, collections of models that you can use and switch between them depending on which one is more accurate or reliable. Okay, so let's talk about closing the loop now, where some of this is applied in practice. Here's an offshore Southeast Asia drilling ship. There's a shallow, high-pressure gas-bearing sands, okay, and that required very fast kick control response. They knew it was going to be an issue, and without managed pressure drilling, this may not have been possible. The desired, we wanted to meet some of those targets that I mentioned before, plus or minus 1 bar in drilling, and plus or minus 3 bar during connections, and also be able to monitor when the mud was not flowing. Now that's not possible with mud pulse telemetry. Okay, so the solution was managed pressure drilling and control system with wired drill pipe. And these targets were met. You can see a schematic here of how this was configured. Okay, so you were changing the choke and the back pressure pump. You had a network controller, okay, and then you have the wired drill pipe, okay, that's going to sense down at the bottom of the pressure sensor, what's happening real time and in high speed data transmission. Okay, a little bit of additional information is right there. Okay, another example is closing the loop in Latin America on land. So this was a severely depleted reservoir. there's a formation fluid influx in upper well sections, and there were well bore stability problems. This required the consistent monitoring and control of bottom hole pressure at all times, including when the pump was off. Okay, again, the solution for this was managed pressure drilling and wired drill pipe. It was completed successfully, again with a very similar setup as we had before. A little bit of additional information is given in this publication. Okay, so just to cover a couple of the main points of this presentation are that automation creates value with high speed and two-way communication. We have predictive controllers where we started with these high fidelity, very accurate models, but in order to be able to compute them real time in real drilling operations, we've had to use lower order models that are trained by the high fidelity or physics-based models. Okay, so one of the needs, and I'll just highlight this, is that MPD service providers and clients need fit-for-purpose modeling. Okay, there's a lot of models out there. We need models that can be used during drilling operations to give real-time advisory to either the driller or to computer systems that will automatically adjust the chokes and the pumps. The next generation automation solutions, the trend that we see in industry is that they are being built upon systems that include telemetry of some sort and real-time data and predictive models as advisory tools with the goal of moving toward full automation. Although there are many obstacles and many challenges, and one of the things in talking to different companies, different researchers, there's a common goal here, and the industry is definitely moving in this direction, although there remain several very daunting challenges, and it's going to require development. There are going to be years in terms of making that transition to full automation. But the future is bright. It's going to require the best minds, but we see a lot of progress happening. Again, with those three things: wired drill pipe or high-speed telemetry, advanced models, and then better optimization algorithms, controllers, automation solutions that are being provided.